I want to talk to you a few minutes about the origin of life and simulations I've been running aimed at uncovering the dynamics by which life may have originated from non-life, and then why I think this may be important for AGI and superintelligence. So let me start with the origin of life side, and I'll get to the AGI side. And I wrote a blog post and published a paper about, or posted online a paper about this recently. But I want to give a bit more of the sort of qualitative side of it here. So, I mean, one of the core ideas in origin of life research is autocatalysis, and I wanna unravel that a little bit. So life doesn't have a completely strict definition, right? Like there's borderline cases in the biology world, like viruses and retroviruses, which are kind of somewhat alive, somewhat not alive on their own, but they parasitize in other systems. But the key criteria people associate with life are metabolism, like the system keeps itself going. It absorbs energy from the environment, uses that energy to move around, to build itself, to fix itself, and maintain its existence. Metabolism and reproduction, meaning the system spawns new systems, and that reproduction could be via sexual reproduction or asexual reproduction. Biology is messy, so I mean, you can imagine, alien life forms that metabolize but didn't reproduce, like the ocean in Stanislaw Lem's novel Solaris or something, right? But as a rule of thumb, metabolism and reproduction are key aspects of life. Speaking of biological life, and in artificial life, I mean, people have tried to make digital systems that displayed robust metabolism and reproduction, but without so much success. I mean, you can get toy models of metabolism and reproduction in computational systems, but so far they haven't had this sort of richness and diversity of form of biological life. And they've seemed sort of shallow and fake, right? And I personally don't think this is because you need biology per se to get life. It's just that digital systems, they've been much smaller in terms of the amount of information that they have in them than biological systems, and that they haven't had the richness of parallel processing that biological systems have. But in any case, autocatalysis is one biochemical model of how you get metabolism, and then from there on to reproduction, right? So catalysis is what enzymes do, right? An enzyme catalyzes a relationship between two other chemicals. So if chemical A and chemical B normally would react only occasionally when they bump into each other, but then you put enzyme C in there. When enzyme C is in there, then A and B react a lot more frequently and produce a lot more stuff, right? So then the enzyme is catalyzing the relation between the other two chemicals, and that's what enzymes do. Now, what autocatalysis means is you have a network of chemicals where each of them catalyzes relationships between each other, right? So every enzyme in the autocatalytic network is catalyzing relations between other enzymes in the autocatalytic network. So the chemicals in the network, the reactions there between, are sort of lifting themselves up by their own bootstraps, right? So you have relatively small autocatalytic network. It's like the Eigenschuster hypercycle that have been known in biochemistry for some time, and I'm in this doesn't give you life yet, but it's sort of the engine that can lead to metabolic processes. And then once you have metabolic processes, I mean, then metabolism plus the right physical setting plausibly can give rise to reproduction, right? Like you had the old Operan model of the origin of life was like you have metabolic systems in little water droplets, and the water droplet gives the initial boundary that lets the metabolic system keep going. It can even reproduce, like a water droplet can divide into two little water droplets. The idea there was that the water droplets were the scaffolding that let metabolic systems remain isolated and persist and reproduce. And then eventually the metabolic system made a cell membrane to strengthen the water droplet, and then it didn't need the water droplet, right? So whether it's water droplets or it's clay and the sort of bubbles popping up in different sorts of primordial clays in the primordial ocean, right? There's been a lot of plausible sounding stories regarding how you get from metabolism toward reproduction. Once metabolism is there, getting to metabolism via autocatalysis seems to kind of be the hard part, right? And so there's been a whole science of trying to simulate autocatalysis, and basically set up a computer simulation of a bunch of chemicals all interacting with each other and let them go and see if you can, in that chemical brew, get an autocatalytic network to pop out, right? And this has not been a total failure nor a dramatic success. And one thing you wonder is, well, maybe these simulations just haven't been tried at enough scale, right? Because, I mean, the primordial sea was big, presumably, so you had a lot of different conditions, a lot of bubbling around chemicals, and eventually, after a long time, some of them became autocatalytic and metabolic. Then they were in clay or water droplets or something, and they then turned into early life forms, and you then got DNA and RNA and all that. But without the scale of a whole, like, digitally simulated primordial ocean, you know, maybe it's just hard for the statistically improbable phenomenon of autocatalysis to congeal, right? So what I thought of is, and this was the simulations I recently ran, what I thought of was taking a more sort of anthropic principle approach. So the anthropic principle is the idea that you take our own existence as a piece of data. Like, okay, we are here right now, and that tells us something about our universe. Like that's evidence, right? So we should incorporate that in a model of the universe. And that's been leveraged in physics. Like, you ask, well, why is the mass of the electron what it is, right? Like, why is the dimensionality of the universe 3? Well, if a certain range of electron mass or a certain dimensionality for the universe are what it takes to cause life to emerge, then you could look at, like, well, okay, maybe there's a huge ensemble of universes with different dimensionalities and different masses for the electron, and maybe most of them didn't work, right? And the reason that we see the mass of the electron as it is, and the reason that we see the dimensionality of the world as it is, maybe this is because we are here, right? And there is no one looking at those worlds with other dimensionalities or electron masses because they didn't work in terms of congealing, complex life forms that could reflect and think. So I thought about origin of life simulations that way. I thought, well, okay, instead of just starting a brew of chemicals and letting it brew and seeing what happens, and wondering if we have a big enough statistical sample to get something interesting to pop out, right? Why don't you take an initial condition, which is a disordered brew of chemicals, then take a terminal condition where we assume autocatalysis popped out, and then say, okay, what would be the simplest path by which you could actually get autocatalysis to emerge? What's the simplest path from history to destiny, right? From no autocatalysis to autocatalysis, from no life to proto-life. And if you look at it that way and run some computational simulations, you find it's not that hard to get simple pathways via which autocatalysis emerges. And that leads me to believe that there's no problem with the spontaneous self-organization of autocatalysis out of brews of chemicals that are kind of changing around in different configurations. The issue is just, you need a big primordial soup for this short path from non-life to proto-life to emerge, right? And I then did some follow-on experiments that look at spatially distributed networks of these evolving chemical soups going from non-life to proto-life, and you can get the emergence of simple self-reproducing, metabolizing systems that way. I also experimented with things I would call morphic resonance-like phenomena. Like the principle of morphic resonance is when patterns have occurred already, they're very likely to occur again. And some people like Rupert Sheldrake or Lee Smolin have posited this as a foundational cosmic principle of the universe. I think, while I'm sympathetic to that, you don't really need that in this context. There's plenty of plain vanilla chemistry reasons why once reactions have occurred in a certain substrate, they're more likely to occur again. So I experimented with this sort of morphic resonance dynamic, and what I found at first was it caused like dumbass first pass simplistic autocatalytic sets to pop up and then not grow too much more. Then when I added what I call morphic anti-resonance, like once a pattern has occurred too much, it's inhibited, right? So pattern occurring a bit, it gets stronger. Pattern occurring too much, it starts getting weaker again. If you add in properly tuned morphic resonance and morphic anti-resonance, then that boosts the probability of getting autocatalytic sets, right? It makes the distribution of the set of near autocatalytic, almost autocatalytic sets much healthier. So it's easier for new sorts of autocatalytic sets to pop up and then become more and more prevalent in the population. So that's a fun sort of simulation to run, and I'm talking now to some friends who are deeper into the biochemistry side and thinking about ways to make the simulations more chemically realistic, although they are real already. There are already real computational chemistry simulations, right? I mean, they're not just toy artificial life type things. Huh? So this is enabled by, Codex and Claude Code, which don't come up with the ideas for me, but they make it much easier to code and run these simulations. Like without LLMs, I would not be able to run simulations of the origin of life in my spare time. I mean, the ideas are clear in my head, but typing and debugging all the code takes time for me or anyone. So, I mean, where we are now, the LLMs are not smart enough to come up with the idea like, hey, let's look at the shortest path between the initial condition of non-life and the terminal condition of proto-life. But the LLM is smart enough to help you structure a software simulation that lets you explore this idea, then analyze the results, and based on those results, go back and reshape the simulation, right? So that's quite cool. Now, what does it have to do with AI, right? And that gets us to a different line of thinking, which I refer to as algorithmic chemistry, and that's a term I learned from a paper from a guy named Walter Fontana, decades ago. And what Fontana was doing decades ago was taking, like, in a computer, a simulated, like, primordial soup of little computer programs, Lisp codelets, right? And he was having these Lisp codelets rewrite each other. So what each program did was rewrite another program into yet another program. And you can have catalytic programs, right, where a program made it easier in some way for one program to rewrite another program into yet another program. So you have this big inter-rewriting program soup. And this was a long time ago. Fontana has recently gone further into more realistic biological network modeling sorts of research. But Kristen Thoresen, who organized our last AGI conference at the University of Reykjavik in Iceland, Chris Thoresen had a programming language called Replicode, where it's rewrite rules to produce other rewrite rules, and a cognitive architecture called ERA, which is wrapped around that. And he got that to control humanoid robots and the Humanobs EU grant-funded program. So there's been work like this over the decades. This notion hasn't yet led to amazing practical results on the level of deep neural networks. On the other hand, it hasn't been tried out ever at the scale of GPT-2 or 3, let alone GPT-5, right? So algorithmic chemistry is one of the many AI paradigms that seem promising and interesting over the decades, but has never been rolled out at massive scale. But now we have the infrastructure to do so, right? So with the Hyperon system, with Meta language and the MM2 Meta 2 language and the Morphic scalable knowledge repository, I mean, we have the framework to try algorithmic chemistry at large scale, right? And we can run it across atom spaces, which can be sort of algorithmic chemistry soups. We can run on atom spaces split across multiple machines using distributed atom space. We can have those machines run, with no central owner or controller, coordinated by SingularityNet platform now, by ASI chain platform soon, right? So we are now moving into an era where we can viably run scalable experiments on algorithmic chemistry for the first time, which is quite interesting. And autocatalysis is a phenomenon that conceptually exists within algorithmic chemistry system, just like it exists within real chemistry systems, right? And that's quite interesting when you place it within the scope of other AI algorithms out there. I mean, an autocatalytic set of thought patterns or ideas. It can be like a self-reinforcing belief system, right? Or it can be a set of procedures for doing things which all help each other to do things better. And the trade-off between morphic resonance and morphic anti-resonance makes a lot of sense here, right? Like in a mental context, you want to grab what worked and keep doing it, but if you do that too hard, you'll never learn other things. You want to reinforce patterns that have worked up to a point. When the pattern becomes too prevalent, you want to start de-reinforcing it to let other things get a chance, right? So you can see, and the reproduction aspect, of course, once some collection of knowledge, some subnetwork of knowledge, or some network that is serving as a useful operating procedure, once it works in one context of your mind, like you would like it to spawn copies that can try to do similar things in other aspects of your mind, right? Like if you come up with a new thought network that's good at planning research projects, well, maybe some copy of that should help you plan trips, or help you plan writing projects or something, right? So the whole apparatus of metabolism, reproduction, autocatalysis, morphic resonance, morphic anti-resonance, like all this makes sense in a cognitive context, just like in an origin of life context. And it seems to me intuitively like there's a lot of creative power here, right? Like it's not that we don't have ways to get computational creativity in our AI algorithms otherwise, right? I mean, we have inductive and abductive reasoning, and abduction is creativity based on creative analogies. Concept blending we have is a different mode of getting creativity based on unexpected analogies and combinations, right? And then we have evolutionary program learning, where you take patterns and procedures that have worked before and mutate them and combine them with each other. And we're experimenting with this now in Hyperon systems. So this is all good, but it seems like these algorithmic chemical networks may have even more creative power than what you get from abductive reasoning or evolutionary learning, right? And the origin of life research, it's different. I mean, we're not trying to get actual AI behavior out of these chemical soups, but it's sort of a playground where you can explore the high level dynamics that may then manifest in algorithmic chemistry systems, in the Hyperon framework. So we're not yet playing with algorithmic chemistry in Hyperon, but I think we're a few months away from really wanting to start with that. I mean, honestly, if we were resourced in Hyperon and SingularityNet to the level of an OpenAI or Anthropic or Google, we would totally have a team of a couple dozen people making algorithmic chemistry function at huge scale in Hyperon, like the infrastructure's ready. On the other hand, we've prioritized getting evolutionary learning, getting logical, uncertain reasoning, and a few less speculative things going first, and once those are running smoothly in Hyperon, we'll try some more wacky stuff like algorithmic chemistry. I mean, there's also trying to get deep neural nets to work neurosymbolically in Hyperon. Now that we have this scalable infrastructure, there's a whole bunch of different really cool things to experiment with, but porting the conceptual lessons from this origin of life simulation into AGI cognition via algorithmic chemistry, it's one of the things on the list, and hopefully not that far off. Super exciting times. It's decades ago, I was reading Fontana's work on algorithmic chemistry, right? And it was mid-1980s in the library at Simon's Rock College, where I did my undergrad work. I was reading about Eigenschuster hypercycles and the origin of life, and started wondering, is there a better way to simulate all this, right? So now we're at a time when all the threads are coming together so rapidly and so remarkably, right? It's really it's a unique time. I mean, as I've said before, in a few years from now, AGIs may be better at this sort of creative discovery than we are. It won't mean humans won't still do it, but doing it right now, there's a certain oomph and importance to it, right? Because we have the slightly frightening but extremely exciting position where, getting these AGI ideas right, getting ethics right, getting creativity right, getting reasoning right, getting control and guidance of AGI systems right, it's not only a super fascinating set of puzzles to solve, but it's perhaps existentially important to our species, and certainly important to the well-being of our species during the transition between here and singularity, right? And after singularity happens, humans solving hard problems will not have the same tremendous import one suspects, because humans will not be the best problem solvers around anymore. So we're in a unique time when, solving these sorts of problems is easier than ever before due to the not quite yet AGI tools available. And also, it's still important for us humans to be working on these things. It's fun, but it's not just for fun, right? So it's anyway, another snapshot here, walking through the park. I'm about to head off to LA for some meetings, but glad to take a few minutes to share this with whoever wants to listen.